You did.
Yeah, there you go.
So I should start over. Yeah. Oh, it's okay. I will start. Over.
Yes, no, everyone can hear you now.
It's okay. Okay, very good. So let me start over. I was just saying that I will talk to you about my research from my first year of PhD study, which involves basically Hecke algebras with non-trivial characters, so twisted Hecke algebras as we call them. And we use these Hecke algebras to examine the p-adic new vectors and new spaces and turn them into classical results. So I start by taking a Dirichlet character of Z and Z and considering the space of cusp forms with weight K, level N, and of course character chi. And our goal, which might seem unmotivated at first, but I will explain why it is this way, is to show that there exists a family of Hecke operators, Ti, with this corresponding set of eigenvalues, lambda I. So lambda I corresponds to Ti is fixed, such that if you take the intersection of the eigenspaces, of the lambda I eigenspaces of these operators Ti, what you get is exactly the space of new forms. So we use these operators to slice away, let's say, the space of new forms from the full space of cusp forms. Now, the reason we do this is because with my advisor, we're working a lot with half-integral weight forms. And basically, we use a lot of the Shimura correspondence. We're trying to get basically a characterization of the new space for half-integral weight. So for us, this the classical definition of the new space as the orthogonal to the Peterson inner product to the old space, it's not sufficient. It's not exactly very descriptive. And this is why our goal is to be able to do this using operators that with the Shimura correspondence we can translate into the half-integral case. And how do we do that? Well, the idea is to go locally, work locally, and use p-adic Hecke algebras and p-adic Hecke operators. So we start then by taking the analog of the modular subgroup. So this is the analog of gamma node n, as you may see easily. And we go work over the Adels. So I recall the strong approximation theorem here, which basically says that every matrix inside the Adels can be written as a rational matrix times a matrix with real coefficients times this subgroup K naught, which is the restricted product of these subgroups K naught P to the n that we have here. So it's unramified at all places. You can think of it as ramified at all places except the primes that divide are n. The n I have fixed from before. Okay, and if you take the character, you can analyze this character. And it's the restricted product of local characters, chi p, with which we will be working on from now on. So the idyllic analog of the cusp forms, of the space of cusp forms, is this space of functions, which are defined over GL2Q over modulo GL2A, quotient GL2A. So, and they have basically, they are right invariant by, right chi invariant by K naught. If anything is inside here, then you can take it out by the character and also the center. And of course, there is a cuspidality condition. There are other conditions which I'm not going to get into because I'm not going to be using them today. And then one can define the Hecke algebra, the local Hecke algebra, which is the algebra of compactly supported locally constant functions. This notation, I mean the double cossets, by the way. So it's left and right quotient by K naught P to the n here. And as I said, there is an isomorphism between these spaces. So the space of cusp form is isomorphic to the space of automorphic forms, automorphic functions. And there is, so you can take the idealization and de-idealization of any form in here that you want. And if you have a function that acts, and if you have any element of the Hecke algebra this diagram is commutative. So any Hecke operator that, anything inside the Hecke algebra, you can view it as a classical Hecke operator, in fact. So let's see an example of this, which is the well-known Iwahori-Hecke algebra. So the Iwahori-Hecke algebra basically has these three generators. It has, obviously, it has the center. There is this involution in GL2QP, and there are these lower triangular matrices. These I don't need for this Hecke algebra, but I will use them later. So the Iwahori-Hecke algebra only uses W1 and WP and the central characters, and it has the well-known relations with the braid relation that we all know. But the most interesting operator is this one. And why is that? Well, if you take the idealization of U1, if you translate it then to see which classical Hecke operator it is, you just get the well-known Atkinen linear involution, which I have just added here. If it's your first time seeing, I'm sorry for that. You're not going to make out what it is just from this. But it's the Atkinen linear involution. It basically is used to lower the level of a form. And this is another well-known operator from Atkinen linear, which is basically, so it's a twisted version of this operator, actually, that we use here. And if you take the de-idealization of U0, you obtain this operator instead, which is UP times WP, the involution from before. Now, using QP without the character, using QP, this QP operator with trivial character, Baruch and Pourquet were able to show that this and this character QP, this operator, sorry, and its conjugate QP, for trivial character and square-free n, they do indeed what I promised you we would do. If you take their -1 eigenspaces and intersect them, this is exactly the space of new forms. And they didn't stop there, so they studied this Hecke algebra where this is the maximal compact Sandburg, so GL2 of ZP, GL2 over the integers. And they found another operator, which also does the trick for non-square-free. So this is the most important fact, in fact, I would say, because for a square-free level, we have, even in the half-integral weight case, we have a new form description, somewhat. But here, for the non-square-free n, this is where the point really is. And so this is their theorem, which says that if basically you use QP and QP prime, and this new operator that they found, and its conjugate, and you take their 0 and -1 eigenspaces, then if you intersect these eigenspaces corresponding to these eigenvalues, this is exactly the space of new forms. So now, motivated by this, what I did was first study this Hecke algebra, which is now twisted by this character chi-p. Now this Hecke algebra is generated by these characteristic functions, as you will see. So these functions are supported exactly on these elements yp that I had two slides before, so this yp here. So they're supported on the characteristic functions of these elements. They're not exactly characteristic, they're twisted characteristic functions. And the Hecke algebra, you get that this is an n minus r plus 1 dimensional commutative Hecke algebra, which is generated exactly by these elements, where the r, let me mention, is the conductor of chi-p, is the conductor of this character chi-p. So inside this this, I want to use it to study representations, induced representations of the maximal compact of GL2ZP that contain chi-p fixed vectors. And chi-p fixed vectors is basically a generalization of just a fixed vector. if you have a representation, basically from K to V, a vector is called chi-p fixed if the representation acts like a character on this vector. And if you study these representations, so this is done in the spirit of Castleman, where he finds an analog of p-adic new forms, basically. And this is like translating these p-adic new forms into how we can use them to go to the real, to the classical new forms. So if you see what this, if you examine the action of the Hecke algebra, you distinguish one element. You distinguish this Vn minus 1 element. And this has these two eigenvalues, -1 and p minus 1. And it turns out that this is exactly the element that we need to slice our space here. So if you take, again, the character and you write it, you decompose it as a character of chi p to the n chi m there, with conductor, again, r strictly less than n. So we need the character to be in primitive, otherwise there are no old forms at all. Then if you de-idealize this thing, you get this Hecke operator here. This thing here with some specific integer entries so that it satisfies determinant 1. And you can see from this that if you didn't work p-adically, I don't know like how you would be able to obtain this just classically. It's very specific. But if we use this now, then we can generalize Baruch and Pourquet's result to the case where the character is now non-trivial. So we need the condition for this. To do this, we need the condition on the character. We need it to be either trivial when chi is not, when p divides n exactly once, so the square free part of n, or in primitive if it is in the rest of it. So if you take the -1 intersection, the intersection of the -1 eigenspaces of these operators, the twisted operators that I introduced before, and this new operator here, and its conjugates with WP inverse WP being the Atkin linear involution, then you get that this, in fact, is exactly the space of new forms as we wanted. And yeah, thank you. I won't take any more of your time.
Any questions, comments?
My collaborator for this is my advisor. For this paper, he told me the problem, but he's not part of it. Like this is on my own. But now I'm collaborating with my advisor and Soma Pourquet, and we are trying to do something very similar for half-integral weight. So we find again the Hecke algebra, and these results are actually needed because you go from this case with the Shimura correspondence to the half-integral weight case.
Anyone? Comments? Questions? If not, let us thank the speaker. We meet in 30 minutes.
Great job.